Okay, next, close to practical scenario. We're looking at electrical field by a uniformly charged infinite plate sheet. So basically we're looking at plate. Okay guys, so let me standardize that. I don't just want to draw that. Again, remember this is infinitely long. It keeps going. And it has charges everywhere. And they are uniform. So here the charge density will be sigma coulomb per meter. Is that correct? Sigma is correct. Coulomb is correct. Square. Area, right? It's 2-dimensional. Next, what is that we are doing? Same funda. First, we need to decide on Gaussian surface. Actually, before that, we need to decide on pattern. What kind of pattern of electrical field are they producing? And then decide on the Gaussian surface. Once we decide that, we will look at the angles and then angles and the surface. Once we decide that, then we will look at, right, flux. And once we get an expression for flux, we'll equate it to this particular expression. And then we'll find the electrical field and some conclusion. That's the funda. So for this, I thought I'll not do it, but I kind of did it off. So that's your plate. That's your field line, but it has to be everywhere. And this plate has to be infinitely big. Right, guys? So any other angle, the field lines will get cancelled. So it has to be a line which is perpendicular to the surface. Okay, so that's your surface and that's your electrical field line. Now, what kind of Gaussian surface should we pick? I'll give you guys different options. Please have a look. So first I'll start off with a cube. Again, you guys have to decide. I'm just showing things around. Remember, there's infinite number of electrical field lines present. That would be your top view. Next, a cylinder. Next, a sphere. So which is the best option? Yes, either a cube or a cylinder. Both are good enough. Okay, so let me increase the size a bit. So if I pick up a cylinder or a cube, why is it good? Why not a sphere? Let me explain that. Sphere, you can see very clearly over here. Look at the area vector. Imagine the area vector, right? In this case, the area vector will be at this point, it will be somewhere in this direction, up and right, northeast direction, right? While this is up, so there's an angle that's not convenient. While when it comes to a cylinder or a cube, they always are at an angle of 90 degree. Can you see that? They're at an angle of 90 degree. Even a cylinder is so. Okay, so the Gaussian surface can be either a cylinder or a cube or a cuboid. So with that, we can just derive, it's not that big deal, then it's kind of convenient. So here we are looking at the Gaussian surface. The electrical field generated by this line charge radiates outward and has the same magnitude at all points, equidistant from the plate, remains perpendicular throughout. So all of these keywords, equidistant and radiating outward, we can't miss. Thus, we use a Gaussian surface in the form of a right circular cylinder. Again, we can use anything, to be honest, a cube, cuboid, or a right circular cylinder. Actually, I wanted to use cube. Anyways, here I've written it as right circular cylinder. And let that have a radius of r and length L. And its axis is perpendicular to the plane. This is keyword. Actually, if you don't write this in when it comes to a cube or a cuboid, it will be okay. Actually, a cube will be okay. So let's look at the flux. So we have this to be positive set of charges on the plate. And here I've assumed the Gaussian surface to be a cylinder. So let's have a cylinder. And this will be a dotted line. Yeah. Okay, so that's your Gaussian surface. And this is of radius r. Actually, I'll write, not writing that. It's okay, but main thing that we have to discuss is we have to look into the surfaces, is it not? So what surfaces can I divide this into? Or what parts can I divide this structure into? One is at the top, one is at the bottom, and the curved surface area. Say somewhere over here. Now let's look at the electrical field lines going through them, right? So we have, remember, they're outward. So it has to be something like this. And here too, it is outward. It has to be something like this. And for this, it will be something like this. Now, area vectors. Let's draw the area vector. So here it would be outward, outward. Again, this is also outward. Actually, that won't be the angle. Something like this. But this will be 90 degree. So this is your E at that point, E at that point, right? And these are placed in such a way that this is the center and the length, this length will be L by 2. Or if I take this entire length as 2L, this will be L and this will be L. And this is your surface 1, surface 2, and the curved surface area, surface 3. So this will be your ds1, ds3, and ds2. Yes, so I'll make this as 2L. Okay. Now, what can we tell? Clearly, electrical field is perpendicular to the curved surface area of the surface. And therefore, we have that theta, the surface 3 to be 90 degree throughout, while it's parallel to S1 and S2, right? Similar pattern. If you guys see the other derivation also, it's similar pattern. Now we're looking at the flux. So this would be EDS, right? Total surface, we're adding up all the surfaces, but we have divided the surface into 3 parts. 1, 2, 3. And here too it is E ds cos of S1, EDS cos of theta S2, EDS cos of theta S subscript 3. So this will be 0. E is constant, and so this is ds plus S1 ds S2. Agree? Now, E, this will be pi r square plus E pi r square. This will be 2E pi r square. That's your flux. Now, we have from Gauss's theorem, the flux through any surface is the amount of charge that it encloses divided by the permittivity of free space. And Q here is, right, it will be equal to what? One is density into the area. What is the area that is enclosed over here? What is this area? That 2 is your pi r square. Pi r square. So from 1, 2, and 3. From 1, 2, and 3, what can I tell? Rho pi r square is equal to 2 pi, sorry, by epsilon naught, 2 pi r square E. So pi r square gets cancelled, and E is equal to, not rho, sorry, this is not rho. This is sigma by 2 pi. Sigma, right? Keep forgetting the term. Okay, so what can we conclude from this? Finally, we'll have to conclude. So what is it telling? Can you see that? It's a very important conclusion. Think about it. It's independent of distance, is it not? It's independent of, and what does that mean? If we have independent of distance, what does that mean? Independent of distance. However far you go, E will be same. That's so weird, right? For a very large, infinitely big sheet, of course, that itself is imaginary. If that was the case, we have a evenly spread out electrical field and it is independent of distance. Whatever is front of the sheet, the same strength is even found at a very far distance as well. That's so weird. But of course, this is for infinitely long. So this is a small note telling that for finite space, not space, sorry, plates, the behavior holds good for the middle region, not for the edge. This is helpful when we are actually building a capacitor and all of that. So yeah, with this we'll derive few things. So we need to know this. Actually, next derivation itself we'll use this. Okay, what did we do? Same funda. We know the pattern of field because we know the forces and how they cancel each other. So we can predict how the pattern of the electrical field lines are. With that, we'll decide on the Gaussian surface. So we decided it to be a cylinder whose radius is r and length is 2l and all of that. The length will not matter because we didn't get a chance to use it in the derivation, to be honest. And we look into the 3 to 4 surfaces over here, in this case 3 surfaces. And we break our surface integral into 3 parts. And then we use Gaussian theorem, get one more expression for the LHS, equate LHS RHS, get your expression for E. And an important conclusion that it's independent of distance. Okay, this is not for your exam. This is only for your knowledge. Note wala. Conclusion part you guys have to. Yes. Okay. Now pause and copy it off end to end.